Number 62. The sun radiates like a perfect black body with an emissivity of exactly 1. Letter A. Calculate the surface temperature of the sun, given that it is a sphere with a 7 times 10 to the 8 meter radius that radiates 3.8 times 10 to the 26 watts into 3 Kelvin space. All right. So we are trying to find the surface temperature, right? We're given the temperature of space here, whatnot. So essentially what we need to do is we know we're going to have 2 temperatures, all right? And we're trying to find then the surface temperature. And we're talking about radiation, so we're definitely going to be using this particular formula over here, okay? So it tells us the power of radiation, the net power that's being radiated, will be equal to the Stefan-Boltzmann constant multiplied by the emissivity of the object radiating that energy, multiplied by the area over which that object is radiating the energy, multiplied by then the temperature difference. Basically, you can think of the temperature of the object, all right, minus then the temperature of the environment. Okay? And they're both raised to the 4th power. Please, only Kelvin temperatures in here. We discussed that in number 55. So in order to find the surface temperature, we're basically looking for T2, all right? We would need to now know everything else, right? So we need to know the net power. Well, they said the sun radiates this power, right? That's in watt. Power's in watts. So you know this value here. Why don't we just plug it in? So this is 3.8 times 10 to the 26th. Stefan-Boltzmann constant, that's a constant, 5.67 times 10 to the minus 8. This one's nice and easy to remember, 5, 6, 7, 8. Okay, then multiplied by E. It says the emissivity is perfectly 1. Now the area, now this is the thing. The surface area, that's what we need. The surface area over which this object is radiating the energy. What's the surface area of the sun? That's what we're talking about. How do you find it? Well, they told us a radius, so how do you connect radius to surface area? Well, the sun is a sphere, right? So the surface area of a sphere is equal to 4 pi r squared. So all you got to do is plug that on in, right? So this is really the surface area. And you can substitute on out, instead of A, you can plug in SA all the time if you wanted, just to remind yourself what it is. But that is basically 4 pi multiplied then by the radius, and they gave it to us, 7 times 10 to the 8, and that's in meters, so we're good. Okay, that has to be squared. And now multiplied by the temperature difference, right? But both of them, they have to be in Kelvin and then raised to the 4th power. So this is going to be T2 to the 4th minus then 3,000, right? That's what that kind of, oh no, excuse me, not 3,000, that's 3 Kelvin. I've been thinking 3K like, K meaning 1,000, that is not, right? The temperature in space is basically almost absolute 0. So this is 3 Kelvin. So literally it's 3 raised to the 4th, okay? Now, why don't we just, so this is going to be 3.8 times 10 to the 26th equals now, let's calculate that whole mess. So we got 5.67 times 10 to the minus 8 multiplied by 4 times pi, then multiplied by 7 times 10 to the 8 squared. Okay. And then, let's just get that answer for right now. So this is going to be 3.49 times 10 to the 11th. Right, times 10 to the 11th, multiplied by T2 raised to the 4th minus 3 raised to the 4th. And why don't we now divide out the 3.49 times 10 to the 11th from both sides? So we'll do 3.8 times 10 to the 26th, divided then by that value. So now this works out to be 1.09 or so times 10 raised to the 15th. And that's going to then equal T2 raised to the 4th minus 3 raised to the 4th. Add the 3 raised to the 4th on over. I mean, is it going to actually do anything? Yeah, plug it into your calculator. Add to that value 3 raised to the 4th. And yeah, it didn't even change any of the decimals that are in my calculator. So then just take that answer and then find the 4th root of it. So do me a favor. Basically take this value here. Okay, I'm going to use the exact value in the calculator, but take that value and raise it to the 1/4 power. Okay, that's how we would get rid of. So we would do 1.09 times 10 to the 15th. Is equal to T2 basically raised to the 4th. To get rid of the 4th power, we have to raise it to the 1/4 power. Okay, so we got to do whatever we do to one side, we got to do to the other. So that's how you're going to get rid of the 4th there and just find the temperature. Okay, so let's raise this thing to the 1/4, and we get now about, this is 5,000 743, so 5,743, or so 744, and this is then going to be in terms of Kelvin. All right. So that would be the surface. That's the surface temperature of the sun. Okay. All right. So now, so that's great. And now letter B. So what is B asking? It says, how much power does the sun radiate per square meter of its surface? Okay. So basically, let's just get rid of all this. Okay. All right. Hopefully you guys are doing well. Enjoying physics, right? Who would have guessed physics could be so much fun, right? No. Physics is fun? No. Of course it is, right? All right. So, So it wants us to find now how much power does the sun radiate per square meter. So basically they told us the power here, right? So let me just write this as letter A. And they told us now the power is going to be 3.8 times 10 to the 26 watts. And then they want to know per square meter. So simply just divide this now by the total square meter, meaning the total surface area. So this we just have to take and divide it by 4 pi times then 7 times 10 to the 8 squared. Okay? And this is then, right, the units are meters square, and you'll see this comes out to watts per square meter. So this is 3.8 times 10 to the 26th divided then by parenthesis 4 times pi times then 7 times 10 to the 8th squared. And we get a value of about now 6.17 or so, right? 6.17 times 10 raised to the, what do we get? 3. It looks like 7, right? Hopefully my eyes aren't going cross-eyed counting all the spaces. And that would be watts per meter squared. Okay, great. So that takes care of letter B. And now what are they asking us for letter C? How much power in watts, okay, per square meter is that value at the distance of Earth, okay, which is 1.5 times 10 to the 11th meters away. Okay, so basically now we know the wattage. So we know the wattage of the sun, right? So now what we can do is essentially, let me see. So let me draw the Earth here. Just pretend that this little circle here is the Earth. Well, that's a square. This little circle is the Earth. Essentially now, what we would need to find is since the sun is radiating energy, and the sun radiates it in all directions, right? If you think about like the energy radiating, that it propagates in these circles kind of, right? Right, because it radiates from all directions. So basically what I'm trying to show here, hopefully this one gets on the screen too. Okay, so what I'm basically trying to show here is that if I now want to find the wattage per square meter here at the Earth, I realize that basically I know the wattage that the sun itself is producing, right? So that again, so for letter C, that's 3.8 times 10 to the 26th watts. But now that total amount of power is being dispersed over a much larger surface area, right? Just think about that. Imagine you were to travel closer to the sun. Would the sun feel hotter? Of course it would. Why would it feel hotter? Well, that's because the wattage of the sun hasn't changed. The rate of the power output hasn't changed. But the rate of power exchanged per surface area here along, remember that this is basically a sphere. I mean, I have a two-dimensional paper here, so I'm trying to do my best. But this is radiating out in terms of a sphere. The wattage per unit area has gone up significantly, right? So as you continually move away from the sun, the same wattage is being output by the sun, but the surface area is basically going up. Not of the sun, but the surface area essentially of these radiated, I'll call them radiation spheres, has gone up, okay? So how do I now figure out the surface area of this sphere on the outside? Well, I would have to know the radius, right? And that's what they told us. They said that it's 1.5 times 10 to the 11 meters away. I'm going to assume that that's from the center of the sun. I don't know it I forgot it off the top of my head. But I'm going to just assume it's kind of like, from, yeah, I'll just assume it's from the center there to the exterior of the Earth. Okay, really won't make much of a difference either way, but that's my assumption here. So then what I have to do is divide this now by 1.5 times 10. Well, excuse me. I have to divide that now by 4 pi, right? Times then, because that's the new radius, this is going to be 1.5 times 10 to the 11th squared. Okay, and that would again be in square meters, and that would tell me the answer. So this is going to be 3.8 times 10 to the 26th divided by now 4 times pi times then 1.5 times 10 to the 11th squared. And what do we get? So here we now have a value of about 1.343 watts, right? Or so 1.34, and that is now in terms of, times 10 to the third, right? Times 10 to the third watts, okay? And then, per meter squared, right? And this would essentially be about, right, 1.34, this is about 1.34 kilowatts per square meter. So if you were to take a square meter on Earth, or, on the surface of Earth, you would look at a square meter, that there's about 1.34 kilowatts of energy being brought to us by the sun. It's not exactly perfectly that, because then you have cloud cover and we have an atmosphere and so on and so forth. So there's certain assumptions that are being made. However, though, you can then figure out, could solar powers be the overall answer? Could that supply all of our energy needs? Quite honestly, if you think about it, everything on Earth, right? Everything on Earth has been supplied through this is through billions and billions of years, but all the energy material on Earth has more or less been given to us by the sun, right? All the energy that's inherent in fossil fuels, they were living dinosaurs, or living fossils long, long time ago. And they ate plants, they ate other animals, but those animals got their food from plants, and the plants got their energy from the sun. I mean, everything, if you start to think about the wood in your fireplace, where did the wood get its energy from? Well, it was part of a tree, and that tree got its energy from the sun, right? I mean, if you start to really think about it, how about you eating whatever food you eat, where the energy that's inherent in the food, where did that energy come from? Well, if you're a vegetarian, it purely came from the sun, right? That's easy to see. But even if you're not a pure vegetarian, you're eating meat, right? That energy that's in the meat, where did that energy come from? Well, that energy came from probably plants somewhere along the way, right? So it kind of all works back to the sun, interestingly enough. Anyway, that's enough of that. Guys, thanks for tuning in. I appreciate it very much. Please remember to subscribe. Give us a hand. We can't do this without you. We appreciate you very much. Take care.